Chapter 6, Chemical Arithmetic, Stoichiometry. So in chemistry, when two different compounds come together to form a new compound, we call that a chemical reaction. So bonds are being broken and new bonds are being formed. And the way that we represent this is by writing a chemical equation. So here we have two examples. Ammonia reacts with hydrochloric acid to produce ammonium chloride. Sulfur trioxide reacts with water to produce sulfuric acid. This is actually how acid rain is produced. So on the left side of the arrow is where we have our reactants. On the right side of the arrow is where we have our products. We generally indicate physical states. So here we have G for gas, S for solid, L for liquid, and AQ for aqueous. This means that this substance here is dissolved in water. So we have a solution. We'll talk more about that later on in the chapter. So we indicate our physical states because when we get into looking at energy changes, there's different energies associated for these compounds depending upon whether they are solid, liquids, or gases, or aqueous. When we are writing a chemical equation, we have to observe the law of conservation of mass, which means that the total mass that goes into the reaction has to equal the total mass that comes out on the product side. We can also look at this in terms of our atoms are conserved, which means that however many nitrogen atoms go into the reaction, the same number have to come out. So this is why we have to have a balanced equation, because we cannot create matter nor destroy it in a chemical reaction. Now, when we studied nuclear chemistry, you were allowed to change one element into another. This is not going to happen when we are doing chemical reactions. So how do we balance chemical equations? First thing that we need to have is to make sure that we have the correct formulas for all things present. So you have to remember how to write your ionic compounds, what it means if you're reading a formula and it's a molecule. So ethane reacts with oxygen to form carbon dioxide and water. Now, we don't know what ethane is. That's an organic compound. I would give that to you. So we have C2H6 plus O2. Remember, oxygen is a diatomic, so it never stands alone. Carbon dioxide, CO2 plus water, H2O. So we have the correct formulas. Now, we have to go in and add coefficients, which means putting numbers in front of the compounds. You are not allowed to change the subscripts. If we change the subscripts, that means we're changing the identity of the compound. It completely alters what we have, and we're not allowed to do that. So down here, it's showing us that we cannot change C2H6 into C4H12. That is not allowed. So we always start by balancing the elements that only appear once on either side of the equation. So we can start with carbon, and we look here, we see there are two carbon atoms on this side. There's one carbon atom on this side. So we're going to add a 2 in front of the carbon dioxide. So next up, we are going to look at the number of hydrogens. Here we have 6. Here we have 2. So we ask ourselves, what do we multiply by? We're not adding here, we're multiplying. So 3 times 2 equals 6. So we'll put a 3 in the front. So now we have both our carbon and our hydrogen balanced. Last step is to then balance our oxygen, and we look at our total count. 2 times 2 is 4, plus 3 times 1 is 3. So 4 plus 3 is 7. 7 total oxygens over here. Only have 2 here, so we have to actually multiply by a fraction. And that fraction would be 7/2. Now, we really can't have half of a molecule, so in order to make this completely correct, we go through and multiply everything by 2 to remove that fraction. And notice when we do that, we're not changing the number in terms of what's going in and what's going out. We still have an equal number of carbon atoms on this side, 4 here, 4 here. So multiplying everything through by a single number doesn't change anything. So we can do our final check just to make sure that we have all of the atoms. We're making sure that they are equal on either sides of the arrow. 4 carbons, we have 12 hydrogens, 2 times 6 here, 6 times 2 here. And then we have 7 times 2, 14 oxygens here. 4 times 2 is 8, plus the 6 times 1 gives us our 14. So this is a balanced equation. Now, we've looked at molecular masses before, or molar masses, but we only looked at them in terms of a single element. Molecular mass and molecular weight can be used interchangeably, and this is looking at adding up the masses of all your elements present in your molecule. Now, when we have ionic compounds, we simply call it a formula mass. You do the same thing in terms of adding up the masses of your elements, but this is representing only one unit of your ionic compound, because remember, ionic compounds are 3D crystal lattice structures. So recall, if we are just looking at one atom, we have a measurement in atomic mass units. If we're looking at a mole of it, then we measure it in grams. So for sulfur dioxide, we have 1 sulfur, its mass. We have 2 oxygen atoms, so we have to multiply oxygen's mass by 2. And we end up with a total here of 64.07 atomic mass units. This represents the mass of 1 molecule of sulfur dioxide. Now, as molar mass says, we are representing how much mass do we have in 1 mole of a substance, and it's always going to be 1 mole. So for any molecule, we can look at the molecular mass and atomic mass units and simply convert it into molar mass, which is just in grams. So 1 molecule of sulfur dioxide is 64.07 atomic mass units. If we have 1 mole, though, now it becomes 64.07 grams. So once again, when we're calculating masses, we're just simply looking at the masses on the periodic table, making sure we take into account how many atoms we have of each of those substances, and then we add them up. So now that we know how to calculate molar masses of our compounds, our molecules, our ionic compounds, whatever they may be, now we use stoichiometry, which is really just a fancy way of saying, how can we convert a mass of a reactant into a mass of a product? And we do this by using the mole method, because moles represent a quantity. You can have 1 mole of iron and have 1 mole of oxygen, and you have the same number of atoms, but they weigh differently. So we're not going to concern ourselves so much with the mass of what's going on. It's the fact that when we do a chemical reaction, so many atoms have to come together. And so when we do chemistry, we use the mole because it's the easiest thing to do. So first things first, you have to have a balanced equation. You're going to convert mass into moles, which we've already done, and I'll talk about molarity later. Then we're going to convert moles into moles, which means we're going to convert the moles of what we were given into the moles of what we want. The last step is going to be moles of what we're trying to find, the moles of what we want, back into mass. And you've done this step before as well. Now, the liters comes into play when we look at molarity. And this has to do with the fact that sometimes, well, often when we do chemical reactions, they are done in water. It's called wet chemistry. So instead of looking at the mass of the compound, we actually have to look at the concentration of what we have present. So our 3-step process, which we're going to go over, converting mass of compound A into moles of compound A. Remember, we're going to divide by the molar mass. And in this first step, we will always see 1 mole here. 1 mole will always go on the bottom in the first step. Oh, sorry, excuse me. 1 mole will always go on the top in the first step. Then we're going to convert moles of compound A into moles of compound B. And the way that we do this is we look at our balanced equation and see what the ratio is. What are our coefficients for these specific compounds? So moles of A into moles of B. And then the last step is converting moles of B back into a mass of B. And once again, we're going to use our molar mass, except for this time we're going to multiply by it. Recall here, this is going to be 1 mole. So when we start our 3-step process, moles is on the top. When we finish our 3-step process, moles is on the bottom. So this allows us to convert a mass of a reactant into a mass of a product, or a mass of reactant into another mass of reactant, to see how much of reactant C do we need to react with compound A. So we can talk about the stoichiometric amounts, which is really just meaning we have exactly what we need for this chemical reaction. I like to bake banana muffins. And so there's a specific recipe that tells me this is the ratio of milk, eggs, oil, flour, sugar, bananas, etc. that I need. In a chemical reaction, our recipe comes from looking at the coefficients. That tells us how many moles of this do we need to react with so many moles of this. So sometimes we don't have enough of one of our reactants. So that's what we would call our limiting. And reagent just means reactant. So limiting reagent is going to be the reactant that is consumed entirely. There will be none of the limiting reactant left over. It is all used up, and it's going to determine the maximum amount of product that we can get. So your excess reagent then is your other reactant, which we have more than enough of. And your excess implies there will be an excess of this left over. There will be some of this reactant left over. And these are important things to do because in industry, some compounds are extremely expensive and some are not. So you use the more expensive compound in the limiting aspect because you know you're going to use it all. And the cheaper reactant then you have left over. So for example, here we have carbon monoxide reacting with hydrogen to produce methanol. There is a 1-to-2 ratio. So for every 1 carbon monoxide I have to have 2 hydrogens in order to react. And 2 hydrogens, I mean 2 hydrogen molecules. So over here, if I count, I have 1, 2, 3, 4, 5, 6 hydrogens. I have 1, 2, 3, 4 carbon monoxide. So if I'm going to react all the carbon monoxide, 4 times 2 is 8. I'd have to have 8 of those, and I do not have 8 hydrogens. So that tells me that my hydrogen is going to be my limiting reagent. I will react all of the hydrogen, which then leaves me with 1 carbon monoxide molecule left over. So this is my excess reagent. And notice I've only produced 3 methanol molecules because I used 3 carbon monoxide. So if I look at this once again, every 1 carbon monoxide I put in, I get 1 methanol out. So since I put 3 in, I get 3 out. Since I did not use all the carbon monoxide, this is all I can do. Hydrogen has limited my reaction. So another important aspect of industry is looking at your percent yields for different compounds, especially in pharmaceuticals when they're creating new drugs. We want to get as much product out as we can per each reaction. So we have what's called our theoretical yield, and your theoretical yield is simply your pen and paper calculation. So the 3-step process that we're going to do of mass to moles, moles to moles, moles back to mass, that mass that you calculate is your theoretical yield. This is saying if everything goes perfectly, this is the maximum amount of product that we can get out. Now, your actual yield is once you go into the lab and you do your experiment, and maybe you spill something, or maybe you don't transfer all of what's in one of your flasks into a new flask, so you lose stuff along the way. So this is your what did you actually do, what did you actually get out. So this number has to be given to you. It is, once again, determined by the actual experiment itself. Now, we have the percent yield, which shows us the ratio of these two things to each other. So you're going to take your actual yield, divide it by your theoretical yield, multiply by 100%, and that tells us effectively how efficient this reaction was. Now, we want our percent yields to be as close to 100 as possible. It cannot be more than 100%. If your percent yield was more than 100, then that would mean that you created mass in your reaction, and that's not allowed. So percent yields are a good way to look at the efficiency of your reaction. And if you're only getting a 50% yield, then you go back to the experiment and say, what can I do better? Should the reaction be happening at a higher temperature? Should it be happening at a lower temperature? If I add a catalyst, can I get more product out? Do I need to change one of the reagents? So percent yield does a good job of letting us know how we can fine-tune our reactions to get as much product out as we need. So moving away from stoichiometry a little bit, we can look at what we call percent composition of compounds. And this is important when we look at empirical formulas and doing hydrates, things like that. So percent composition, I'm looking at each individual element within the compound, and this little n here is going to be the subscript. So your n is your subscript for whatever particular compound that you're looking at. If I have ethanol, C2H6O, I can look at how much of the total mass comes from carbon, how much comes from hydrogen, and how much comes from oxygen. Percent compositions for different compounds will be different. So I have 2 carbon atoms, so I multiply by 2. 2 times the mass of carbon, and the 46.07 came from adding up 2 times 12.01 plus 6 times 1.008 plus 1 times 16, because that's the molar mass of the compound. So when I do the math, multiply by 100, approximately 52% of the entire mass of this compound comes from carbon. And you do similar steps for each of the elements that are present. So I calculate for hydrogen, 13%, calculate for oxygen, about 35%. When you add all these percentages up, they should equal 100. Now, when we do our math and rounding and things like that, sometimes we don't get exactly 100. Sometimes it's 99.8 or 100.2. That's acceptable in terms of answers that are going to be okay. But if you end up with something and you have 110% or only 90%, somewhere along the way you messed up your calculations. So carbon, hydrogen, and oxygen can come together in more than just forming ethanol. They can form ethers, carboxylic acids. So there's always going to be a different percent composition for carbon, hydrogen, and oxygen when you're looking at these different compounds. So this allows us then to potentially identify what particular compound we might have. And this is how we do this. If we're given a percent composition, we can then find the empirical formula. Recall, empirical formulas are your simplest whole number ratio of atoms in a compound. So it tells us nothing about the actual molecular formula or the structure of the compound. It just tells us the number and type of atoms that are present. So we take our mass percents, and we're going to assume that we have 100 grams. This is the easiest way to do this calculation, because if you have 50% of something, and I'm saying I have 100 grams, and that means I have 50 grams. 25% would be 25 grams. 37% would be 37 grams. So then we basically are just taking our percentages and saying this is the amount of mass that I have. So you're going to do a conversion, and that is converting your grams into moles. And once again, we're dividing by our molar mass. So now we have a list of the different number of moles of each of the elements present. You will take the smallest number of moles and divide it into all of the other. This is how we get our simplest whole number ratio. So now we have our mole ratio of our elements, and whatever those mole numbers are, we simply change into integer subscripts. So we can never have a half or a third or anything like that. They always have to be whole numbers. If it doesn't come out to a whole number, for example, if you get 1/2, you have to look then at multiplying through everything to make sure that we get whole numbers. So if you had a half of carbon, half a mole of carbon, we multiply by 2 so that we can have 1 mole of carbon. But we would also have to carry that out and multiply all of our other elements' number of moles by 2 as well. So once we have our subscripts, we simply can write our formula. Say it's C2H4O2. So mass percents into empirical formulas. Once again, it's just a series of steps of conversions. Mass to moles, moles into a simpler number of moles, and then our moles go into our subscripts. Another way that we can determine empirical formulas is by combustion analysis. So once again, this is normally looking at some type of organic molecule. We don't know what it is, but we're going to try and figure out what the empirical formula is. So once again, we don't know how the atoms are bonded. So what do? Here we have oxygen coming in because combustion means that I'm going to burn the substance. Here's my heat. So ethanol goes in. And then what we have here are 2 different types of material, one that's going to absorb water and one that's only going to absorb our carbon dioxide. So we start with some mass of this at the beginning, and then we have a new mass at the end because it absorbed water. So we can then determine the amount of water that was produced. We can do the same thing with carbon dioxide. And then the unused oxygen comes out. So you have to be given data in order to do these calculations. I start with 11.5 grams of my reactant. I end with 22 grams of carbon dioxide, and 13.5 grams of water. So what are our steps in this process? Going to be doing some conversions. So I'm taking the mass of carbon dioxide, turning into moles of carbon dioxide. Then, because I'm not concerned with carbon dioxide, I'm concerned with how many moles of carbon do I actually have, because however many moles of carbon come out in carbon dioxide is the same number of moles that have to go in on the ethanol side. So I convert carbon dioxide moles into moles of carbon, and this is a 1-to-1 ratio. Once I have my moles of carbon, I can find my grams of carbon. I'm going to do a similar set of steps, but with water. Grams of water into moles of water. And remember, in this first step, we're simply dividing by molar mass. Now we have to go moles of water into moles of hydrogen. Here, I see there's 2 moles of hydrogen for every 1 mole of water, because there's 2 hydrogen atoms for every 1 water molecule. So here I'm actually going to have to multiply by 2. Where here it was 1-to-1, now it's 1-to-2. So I multiply by 2. And then I'm going to convert my moles into grams. So once again, this last step here is multiplying by molar mass. Here we were dividing by the molar mass of carbon dioxide and water. Now we are multiplying by the molar mass of carbon and hydrogen. So once I have calculated my grams of carbon and grams of hydrogen, I still have to figure out how many grams of oxygen I have. The way to do that is to look at your initial mass of your sample and then simply subtract your total mass that came out from carbon and hydrogen. So now we have grams of oxygen, which then we can convert into moles of oxygen. How do we do that? Divide by the molar mass. So I have within these calculations my moles of carbon, my moles of hydrogen, and my moles of oxygen. Now we're looking at what we did in the previous slide with empirical formulas and simply dividing by the smallest number of moles that were calculated to figure out what our integer subscripts are. So then we have our simplest whole number molar ratio, and we write it out. The last part of this chapter deals with solutions, and as I stated in the very first slide, that symbol of AQ means aqueous, where we've dissolved a substance into water. So we have to represent how much of that substance we have in water. And the way we do that, or one of the ways to represent concentration, is with molarity. And by definition, molarity is the number of moles of solute divided by 1 liter of solution. So our units for molarity are moles per liter. How do I create a solution? When I go into the lab and make sodium hydroxide, a sodium hydroxide solution, that's a strong base. I take a specific mass of sodium hydroxide and I dissolve it into water. And it's a calculation that I do in order to figure out that I'm making the correct solution. So here I start with my pre-weighed substance. This is a volumetric flask. Here is the marker that shows me the exact volume that I need to get to. So I pour some water in, I stopper it up, I shake it to dissolve, and then I continue to add water until my meniscus hits this line. So then I've created some volume of a specific concentrated solution. So once again, molarity is looking at moles per liter. And when you're doing stoichiometry with molarity, we're not going to be using molar mass anymore. You're actually going to be using concentration and volume, because we'll see that a molarity times a volume gives us a number of moles, which is really what that first step is about, converting mass into moles. Well, now we can convert molarity into moles. So if you make a really concentrated solution, you can dilute it. And a dilution is simply adding more solvent. And for most of the chemistry that we do, that solvent is water. So when I dilute something, I still have the same amount of substance dissolved. My number of moles doesn't change. Simply the solution, the amount of solution that I have is changing. So moles of solute before dilution have to equal the moles of solute after dilution. So this big capital M here represents molarity, and then my V is for volume. So my initial molarity times my initial volume is going to equal my final molarity times my final volume. Now, when we look at this, on this side of the equation, this value will be bigger than this value. My concentration before I do a dilution is higher than when I finish the dilution. Now, just the opposite, my volume here is going to be lower than my volume here because I've added water. So I expect to see a larger volume with a smaller concentration. Whereas when I started, I had a larger concentration with a smaller volume. So the last bit of analysis that we can do here, what we call titrations, and we will do one of these in lab. A titration is looking at doing a reaction and trying to figure out the concentration of an unknown solution. So usually we do acid-base. We can also do redox. But we're trying to figure out what is the concentration of this solution that we have. So in order to do that, we have to start with a standard solution. And your standard solution is that solution in which the concentration is known. And normally it's standard because there's already been a titration that has been done on that in some manner to make sure that, yes, this is the exact concentration of the solution that we made. If I go back here, I can calculate what the concentration of this solution of this sodium hydroxide is that I made. But if I truly want to know what the exact concentration is, I can react it with another substance, for example, KHP. Titrate it and say, okay, I thought I made a 1 molar solution. Turns out it was really 1.10 molar solution. So I standardize my solution and I put that into my burette. So my standard solution goes into the burette. The unknown solution will go into your Erlenmeyer flask. And what we are going for is looking to reach the equivalence point, because when we are at the equivalence point, we're at the stoichiometric point of the exact number of moles of our base have been added to neutralize our exact number of moles of acid that we have present down here. That is the equivalence point, when our moles have canceled each other out. The end point of the reaction comes when we see a color change. So your indicators are weak acid, weak bases, and effectively what they do is they are one color when they're in an acidic solution, and they are a different color when they are in a basic solution. So that's how we know. We start with an acid, and an acid it's clear. Once we've added enough base to completely neutralize all of our acid, that next drop of base would then react with the indicator and it turns pink. So we want to try and get our end point and our equivalence point as close together as possible. And once again, this will be a series of calculations, and you're going to be using molarity and volume, because we're going to start with a known volume in our Erlenmeyer flask, but we don't know the concentration. We start with a known concentration of solution, but we don't know until we finish our experiment how much volume we've added. So once we've reached the end point of our experiment, I know the molarity of what's in the burette. I now know the volume. Molarity times volume equals moles. So the moles of acid, or the moles of base that went in had to neutralize all of the moles of acid that were present. So we can do a mole to mole conversion there. Once we have calculated the number of moles that were present in our solution, we know the volume that we started with. So now we can do moles divided by our volume in liters and get our concentration for our solution that was unknown. So within this chapter, it is a lot of math, but most of the conversions we've already done. So we're going to do lots of practice, lots of problem solving. You'll have to be able to do that three-step process of converting mass to moles, moles to moles, moles back to mass. We'll be doing percent composition calculations, empirical formula calculations, both from percent compositions and combustion analysis. And we will also work on doing some titration problems. So practice your math. Good luck.